This is an example, our first example for conservation of momentum in collisions and maybe conservation of energy, although we're going to find in this one that doesn't really work. But we have conservation, or we have a collision in which two train cars, and I'll say this is a pretty standard physics way to talk about this because we know that train cars, when they hit, are going to stick together. Why? Because they have these things on them called couplers, right? That's the point of a coupler, is to couple up the train cars. So I'm going to do this in a number of cases. I have mass 1, one car, mass 2, the other car, and then after they couple up and move as one, I've got a total mass of mass 1 plus mass 2. So because they're coupling and moving as one, we can identify this as an inelastic or perfectly inelastic collision. And so what we expect is that momentum is conserved, kinetic energy is not, because that's what a perfectly inelastic collision does. Okay, so a standard way to ask this question, although this is just an example, would be given some initial velocity of m1 and knowing that m2 is actually sitting still, initial velocity of 0, what is my final velocity of my system put together? To handle this, I've already alluded to my process. I'm going to do this with conservation of momentum. So for this one, I'm going to start from the beginning. P initial is equal to P final. And when I write this, what I really should be writing is this. I'm typically going to leave off the sigmas, but we're looking at the momentum of the whole system. So what is our system? Well, if I've got two objects colliding, in this case at least, it's going to make sense to define my system as both objects. So I've got to look at the momentum of both objects here, the momentum of both objects afterwards, although this is really now just one object, but I'm looking at the momentum of my entire system. So initially, what is the initial momentum of my system? It's the momentum of my first car plus my momentum of my second car. So let me just write this down, m1 v1 initial. And I will warn you now, subscripts are going to get a little annoying. m2 v2 initial, that's my total momentum of both of these objects. Again, this is just one dimension, but I only have a one-dimensional problem, so I'm not going to bother subscripting with x's or y's, but you can if you need to. So this is the left-hand side, total momentum before. This has got to be equal to the total momentum after the collision. I now have an object with a mass of m1 plus m2, traveling at some v final. Now, as I've given this, I've shown v final to the right, and because of this specifics of this problem, I'm pretty confident that that's correct. Total momentum before the collision is directed to the right. Therefore, if I'm going to conserve it, total momentum after the collision must be directed to the right. Right? The total momentum is directed to the right here because m2 has none. Right? M1 has momentum to the right, M2 has no momentum. So if the total momentum is to the right here, it's got to be to the right there. So I'm pretty confident in my V final pointing to the right. Now this is my general equation. What can I get rid of? Well, V2 initial is equal to 0, so that term is going to go away. And I'm left with two terms which I can immediately solve for V final by dividing out the parenthetical masses. V final is going to equal this term m1 over m1 plus m2 v1 initial. Another way to think about that, of course, is p1 initial, which is m1 times v1 initial over m1 plus m2. This is actually really handy to think about in future cases. Until we get an intuition for it, I'm going to stick with this one because we can see a lot of physics happening here. But this actually turns out to be a pretty useful form later. So I just wanted you to see it. You can think about it as you're working through these problems. But we're going to go back here and see if we can get some intuition. First of all, let me say this is the final velocity of both objects. This is the velocity of the first object initially. Now, again, this is all the special case of V2 initial being 0. But if that's the case, then this equation is valid. And let me just call your attention to the coefficient here, the ratio of the masses. This is always, always, always less than 1. How do I know? Well, masses are all positive. There's no such thing as a negative mass, not at least in this universe. So m1 over something bigger than m1 is always going to be less than 1. The denominator is always larger than the numerator. So the final velocity here, is always going to be some fractional value of this initial velocity. That's got to make some sense. Nobody expects these two to couple up and then start moving faster. That violates all sorts of physical laws. In this case, we find that the final velocity of everything together is less than the velocity of the first object. Again, that's for the special case of this one being 0. But if you think about it, I think that's going to make some sense to you. So we've got this final velocity equal to this fraction of the initial velocity of the first one, which was the only one moving. And that the ratio of the masses plays a role. I hope by this point in the semester we see that mass is pretty important. I hope this is not surprising. The ratio of the masses is going to determine the relative speeds of the initial and final states.